So hi everyone, I'm Karolina Halys from Digital Quantum Matter Lab. And today I'm going to talk about cool states of matter. And that is about how cool can we go and how are we cooling things to the extreme temperatures. So the coolest it has been in Waterloo in this year was 238 kelvins. But it can get even worse than that. If we would go to the Antarctic, we would find out that temperatures down there are getting down to 183 kelvins. But we can get even cooler than that by leaving Earth and going to the vacuum of the space. In the vacuum of space, temperatures are reaching 2.73 kelvins. And there is not a lot of particles in there, so you would probably think, can we get even cooler than that? And that's actually a very good question on which I would like to stop here, because it seems a bit contrary to the first law of thermodynamics to get even cooler than that. Because energy cannot be created or destroyed. It can only be transferred from one object to another. So how could we get even cooler than that? First, we'll go back to this question, but first let's talk about the people that were first thinking about the absolute zero. And that was, for example, Lord Kelvin on the beginning of 1848. He was inspired by the Carnot engine that started Industrial Revolution, and he created this formula for efficiency of Carnot engine. This is eta is equal to 1 minus Tc divided by Th, where Tc is the temperature of the cool reservoir, and Th is the temperature of the hot reservoir. So he found out that the efficiency of such an engine would be maximum in the case if Tc would be equal to 0. And that gave him a first hint. But he still had a problem because he didn't know how to relate it to any other existing temperature scale. So with help from those two experimentalists, those are Guy and Charles, and they created Charles' law that is describing how materials are shrinking or expanding under the influence of the temperature. So here you can see volume of the gas is increased or decreased by this coefficient of expansion and Tc, which is temperature in the centigrade. So here alpha is equal to 1 over 273, and Lord Kelvin realized that in case of the absolute zero, the volume of his substance will be minimal. So he wanted this bracket equal to 0, and that happens only for temperature equal to minus 273 degrees. So that's how he set his scale on the temperature in the centigrade plus 273 degrees. So we have our theoretical answer. Absolute zero does exist, but does it exist in experimental sense? Can we get even lower than 2.73 kelvins? And the answer is no, but you can get quite close. And that's quite how close we are getting at my lab, in Digital Quantum Matters Lab. It's 8 millikelvins, so we are quite close. But how do we do that? We are using dilution refrigerators. And dilution refrigerators, as the name suggests, use dilution process for cooling. They are standard in both industry and academia to cool bodies to extremely low temperatures. Here you can see the control panel of such a dilution refrigerator. And the dilution refrigerator itself, it is suspended on these metal beams. And it has cans outside. Those metal cans are there to protect the system from the radiation and also act a bit as a Faraday's cap to the system inside. But what is really interesting is inside of the dilution refrigerator. So if we would take off all of those cans, we would see the dilution refrigerator inside. Topmost can is 50K can because it reaches 50 kelvins. Then we have 4K can that reaches 4 kelvins. Cold plate reaching 800 millikelvins, mixing chamber reaching about 80 millikelvins, and experimental space that reaches 8 millikelvins. Here you can see all of the wiring responsible for communication with our experimental sample and our circuit that we want to measure. But here is the cooling unit that is responsible for main bit of cooling in our dilution refrigerator. Soon we are going to see how it works. But first, let's talk about the gases involved in the cooling process. So those are two isotopes of helium. One of them is helium-3. It's extremely expensive gas. There is a finite amount of it on Earth, about 1,000 kilograms to be exact. So it's also very expensive. And its core consists out of 2 protons and 1 neutron. One of the proton has a spin up and one of the proton has a spin down. So it gives total proton spin equal to 0. and neutron has either spin up or spin down. So at very low temperatures, they are following the Pauli exclusion principle, and they are, so two of those cannot be in the same energetic state in the lowest temperatures. But then we have another isotope of helium that takes part in the dilution process, and that is helium-4. Helium-4 is very common on Earth and not very expensive. It is made out of, the core of helium-4 is made out of two neutrons. One of them has a spin up and one of them has a spin down. That gives total neutron spin equal to 0. And one of the protons has a spin up and the second proton has a spin down. That equals total proton spin equal to 0. So in total, the spin of the helium-4 is equal to 0. And that gives it special property because it becomes a boson at very low temperatures. And it's quite amazing because other bosons are mediators of the interactions, and that's exactly what helium-4 is. So you can see here a list of other bosons for your reference, as for example, photons that are mediating electromagnetic interaction, or weak force mediated by the W boson. And now we have also helium-4 in dilution refrigerator that is mediating this sort of interaction. Those particles are also very special because they are becoming described as Bose-Einstein condensate. That means that as temperature is getting lower and lower, so in this direction, they are starting to behave like one body, although they consist out of many particles, and they start to have a wave function, just as a quantum body. But now we can talk about how the dilution process works. So here on this graph, you can see concentration of helium-3 on the x-axis and the temperature on the y-axis. So, on the left-hand side, we have the quantum liquid helium-3 and helium-4. And on the right-hand side, you have normal fluid helium-3 and helium-4. The whole dilution process starts about 2.3 kelvins. And this black line in between is called sometimes lambda line, because it has the shape of lambda letter. And sometimes it's called coexistence line, because at this point, both quantum liquid and normal liquid coexist. And what we have to do to get the dilution is go down with the temperature to about 1.5 kelvins. And then we can either go right, because we can't get to this blue space. So we can either go right and be in a spectrum of normal fluid. It's called helium-rich phase. Or we can go left and be in a helium-poor phase. And this change of the phases between left and right, oscillation between the phase boundary, is using the energy of the system. So this energy is kind of absorbed from the environment of the fridge, and that's how we can reduce the temperature of our environment to such a low temperatures. Here you can see a place that it takes place. So those are main components of the dilution refrigerator, still and mixing chamber. So it's quite literally heart and lungs of the dilution refrigerator. Everything starts on the small pipe that is pumping the helium-3 rich concentration inside of the mixing chamber. Here on the bottom of the mixing chamber, we have a high concentration of helium-4. And they are mixing with each other, causing the absorption of the energy from the environment. As the energy is absorbed from the environment, it is moving up through all of those heat exchangers and absorbing a bit more energy and mixing up to the steel. Temperature at the, pressure at the steel is very high, and it's good for the vapor pressure of the helium-3. That is because vapor pressure of helium-3 is much lower than vapor pressure of helium-4. So helium-3 gets separated in its concentrated form down to, and is ready to start the process again. This process happens hundreds of times in a dilution refrigerator until the moment when we are reaching temperature of the absolute zero, close to absolute zero. And that is not the end of the story. The whole story is much longer than that, and it takes 24 hours, sometimes even 36 hours. The first 16 hours are dominated by the cooling with the pulse tube. Pulse tube is this device on the right-hand side, and it's not very special. It is using liquid nitrogen to cause cooling, and then we have this specific place where we can see energy temperature spike in our system. That is because all of the gases are getting admitted to the system, so it spikes. But as they are circulating around our dilution refrigerators, we can see that mixture slowly cools down. As it cools down, it changes the form. It stops being a gas and it starts to become a fluid. And there is a point when 100% of our mixture become a fluid, so we have only helium in a fluid form inside of our dilution refrigerator. And then dilution process that we just were talking about starts, and we are able to reach those extreme temperatures. So we reached the states beyond the human imagination. We pushed the boundaries of what we can do and what nature can do, but it just brought us more and more questions. We still have problems with qubit coherence, qubit error correction. We still don't know too much about two-level system and 1/f noise. And those are some of the mysteries that will be there for you to solve. Thank you.
Okay, we have time for a few questions.
So I want to know about how and where is like the helium-3 and helium-4 like obtained from, and like how do they like get it?
So that is actually a very good question. So as I said, helium-4 is less expensive counterpart. So it's much easier to get helium-4. So starting from that, it's the same gas that, when they are giving you a balloon to just like take a breath and have this funny voice, this is helium-4. So that is what we are kind of using. So it's not very expensive. But if it comes to helium-3, the very small amount of it is on the crust of the Earth. And we are getting it from the waste of, for example, atomic weapons. And that is what is used to sell to industry and to sell to academics most often. But other than that, they are just in stars. But because of the logistic reasons, it's hard to get it from there.
Yeah, so you showed the phase diagram and how it relates to the concentration of helium. And I think you said the oscillation around that disallowed zone is how you cool the temperature.
That's right.
What's the reason there is such like a large zone that can't be attained?
What do you mean? I mean, the actual concentration between helium.
I think it was a big purple blob.
Yeah. So as you can see, so this is actually a very good question. So the graph here is finishing about 0.3 kelvins, and here the concentration in the helium pure phase, the helium-3 can get down to almost 0 kelvins. So we assume that with rich phase helium, we could never get to the 100%. We could only do it with pure phase of the helium. And the reason why there is such a big jump, it just depends how much of the helium you have inside of your dilution refrigerator. But sometimes you can have a bad ratio of the helium, and then if you don't, and then this line can move to other position, and because of that you can never reach dilution process, so you can never be able to cool your dilution refrigerator. It's actually a problem very often because helium-3 is so expensive that people often, when they lack some gas inside of the dilution refrigerator, they just load it with a cheaper helium, and then this line kind of moves, and it's much harder to cool the fridge to the point that it's not possible to cool it anymore.
Thank you.
Thank you.
I was gonna ask, you say we've gotten really close to absolute zero, but what's the point? Why are we trying to obtain absolute zero in an object in the first place? What's the applications? What's its usefulness to us?
Oh, that is another very good question. So, very important point is in reality to obtain superconductivity, and this is the stage of the bigger order. So, if you really want to see how the particles are created, like material order and stuff like that, if you really want to see, for example, what affects because, qubits, superconducting qubits, they are very small. So very small changes might influence the noise of the system and stuff like that, So if you really want to see, for example, how other materials that don't have to have a perfect structure, like a cubic structure that have all of the atoms, there might be some, gaps in your material and stuff like that, how it often happens in silica. This is most popular for in current technology. Then you really want to go low to destroy this thermal noise as much as you can and see the actual properties of the material and not only the effects of the temperature.
Thank you.
Thank you.
Can you go back to the dilution fridge slide?
This one?
Before?
That one?
Yeah, can you explain like how the circuit of that works?
Okay, that will be a bit complex given the time constraints, but I can give you like a quick kind of like overview. So you can see this small square there, and like inside of the dilution refrigerator, you have a lot of valves, and this small square rectangle is showing you everything that is going on in dilution refrigerator. And those buttons here are different valves. So you can open system or close system if you don't want helium-3 to go in a certain areas. Because there is also a lot of pumps involved in this system, and sometimes maybe it's not very safe to open the certain valve, because you could, for example, remove the gas outside of your dilution refrigerator. And here is the container with the gas. So everything starts in here. And here is, for example, the access to the vacuum can. So like the topmost can. So if you want to remove the topmost can, you have to kind of remove all of the remove the pressure from all of the, let's say, valves on its way. Because, the whole system gets pressurized and it gets to the vacuum, like, to the pressure of the vacuum. Yeah, so that's mostly how it works.